Yesterday we talked about the mean solar time and also sidereal time. While discussing that, I forgot to mention why there is a difference between the two times. Now we defined the mean solar time. Similarly, if we consider the average of the multiple observations of sidereal time, we get the mean sidereal time. Now let's quickly understand why there is a difference between the two times, mean solar time versus mean sidereal time. Now we first calculate the measure the sidereal time using a distant astronomical object and then mathematically convert it to solar time, right? So basically, solar time is the time that an observer, hypothetical observer on the sun would see as the time that the Earth requires to complete one rotation about its spin axis. So let's draw the Earth orbiting the sun. So this is the sun, and let's say this is the Earth. Okay, and let's say there is an observer on the Earth. At some time, he is seeing the sun on top. Okay, so sun is overhead at this point in time. Now the Earth rotates about its spin axis. During that time, it also moves in its orbit around the sun, right? So let's say after one complete rotation about its spin axis, the Earth is here in the orbit around the sun. Okay? So this was the old position before rotation. And this is after rotation. So after one full rotation, the same observer is here now. This was the line connecting that observer and the sun. Okay. Now since the sun appears as a disk, you can pick one particular point on the sun and then connect that point with the observer. So after one full rotation about the spin axis, the same observer is here, and this same line which I drew here, the same line is here. But at this point, the observer would not see the sun on top. So the Earth has to rotate extra for the observer to see the sun on top. And how much extra rotation the Earth has to make to see the sun on top again? Let's say this is the angle theta subtended by this segment at the sun. So this much distance the Earth has moved in its orbit around the sun. The same angle extra the Earth has to turn to see the sun on top again. Okay. Now since we are interested in mean solar time, let's say we consider the average time the Earth requires to complete one orbit around the sun. Okay, and it is 365.25 days. Okay. We are interested in finding this angle theta. So how much will it move in a day? So it moves 325 in 360.25 days. So theta will be 2 pi by 365.25. So this is a angle theta. Now let's say omega is the earth rotation rate. As seen by an observer in a distant star with respect to inertial space. This is the earth rotation rate omega. So one mean sidereal day is 2 pi by omega. This is the time period, right? So this much time the earth requires to complete one rotation about its spin axis as seen by an observer in an inertial space. And omega is the mean average. Yeah. But how about the solar day, mean solar day? In case of mean solar day, the earth has to rotate some more angle, right, theta. So it is 2 pi plus this angle 2 pi by 365.25 by omega, whole thing omega. This is the extra angle that the earth has to rotate about its axis to see the sun on top again. Now let's take 2 pi out. We have this. So this one is one mean sidereal day. And this factor is about 1.0027. So this also indicates that the solar day is longer than the sidereal day. We know the length of a sidereal day is 23 hours 59 minutes and 4.09 seconds, whereas mean solar day has 24 hours. How to relate this hours, minutes, seconds when we consider these two different lengths of day? So let's say one mean solar day is equivalent to 86,400 mean solar second. So this is actually 24 hours. 24 mean solar hours. Okay. Now one mean sidereal day is equivalent to 86,400 mean sidereal second. So again, one mean solar day has 86,400 mean sidereal second. Okay. Now, when we say mean sidereal day is 23 hours, 59 minutes, and 4.09 seconds long, we calculate everything in terms of solar hours, minutes, second. Okay. So let's convert this one to solar, mean solar second. So this is 23 hours, so everything will convert to seconds. So basically 23 hours that will convert. 59. Okay, so this is actually less than 86,400. So it's actually, if you do the math, you will find that this is 1 by 1 mean solar second. So on this side you have 86,400 mean sidereal second, and this side you have this one, this whole thing will come here. So I'm not writing the whole thing again. Whole thing will come and then mean solar second. And this one is less than 86,400. So 1 mean sidereal second is equivalent to 1 by okay, so this is how we can relate the sidereal second to solar second. Okay, so everything is derived from the day, length of a day, whether it is mean solar day or mean sidereal day. You can derive the length of a second from that. Okay, so from the mean solar day we get the mean solar second, and then from the mean sidereal day we get the mean sidereal second. This is how we can relate the two lengths. Any question? Okay. Next we are going to talk about GPS and IRNSS time. Yesterday we talked about the UTC, Coordinated Universal Time. UTC follows calendar day format. Calendar day, month, year, hour, minute, second format. 1, 2, 3, 4, 5, 6, 6 wheels are there. Okay. Now these two systems, GPS and INSS, they have a different time scale with 3 fields. They do not follow UTC format. There are constellations that follow UTC format, but these two constellations do not. For example, GLONASS follows UTC format, but GLONASS is 3 hours ahead of the UTC. Okay, Beidou is tier 2 UTC. But both GPS and IRNSS have different formats with 3 fields. What are these 3 fields? Time of week, week number, and then call it WN, and then week number rollover. Okay, time of week tells the seconds in a week from the midnight between Saturday Sunday of the preceding week. Okay, so it is reset to 0. I'm writing here every midnight between Saturday and Sunday. Okay, and then it is counted again. Okay, so every midnight between Saturday and Sunday it is reset to 0. So when it is reset to 0, week number is incremented by 1. Let's call this TOW. This is the abbreviation for time of week when TOW is reset to 0. Okay. But what is the maximum week number that can be held? Week number and time of week format are used to broadcast time in. Okay, so when the ephemeris is transmitted in the nav data, the satellite has to post time to it. It has to be tagged with time. So that is called time of ephemeris. Similarly, the clock correction parameters also have a time tagged with it. It's called time of clock. So for this time, the week number and TOW are transmitted in the navigation data. And there are 10 bits allocated for the week number. We know that each bit can take one of two values, right? Either you can consider 0 or 1 or plus minus 1. So basically it can take one of two values, right? It is binary in nature. And there are 10 bits allocated to it. So the total values that can be represented using 10 bits is 2 to the power 10 values. 2 to the power 10 values means 1024. Week number starts from 0. Okay, so we can have 0 to 1023 week number because of the limited number of bits assigned to the week number. So there can be 1024 values, different values of week number, and since it starts from 0, it can take a maximum value of 1023. So when the week number reaches 1023 and it is incremented by 1, it is reset to 0. Okay. When the week number is reset to 0, this is incremented by 1. Week number rollover is incremented by 1. Okay. So week number rollover holds how many times the week number field was reset to 0. That's why it's called week number rollover. Okay. Now, these three fields, week number, rollover, week number, and time of week, they must start from a certain time. The time when the GPS time started, the time scale started, is called epoch. And it is So at midnight between 5th and 6th June 1980 UTC, GPS time started. So this time is the GPS time clock. Okay. Since then, GPS has undergone two rollovers. The last one was in 2019. Okay. GPS has undergone two rollovers since its epoch. IRNSS time started at midnight between 21st and 22nd August 1999 GPS time. So at this time IRNSS time started. Okay. The IRNSS has gone one rollover since then. The GPS has undergone two rollovers with number rollovers. And IRNSS has one rollover. Okay. Now the navigation data does not broadcast the rollover. The receiver internally has to keep track of the rollover to give the time properly. Okay, the receiver software is configured to keep track of the week number rollover, and the week number and time of week are calculated. Even you can go back and forth between UTC and the two time, the GPS time and IRS time, using some simple algorithm. Okay? So given UTC, the receiver can calculate the week number, time of week and week number, and vice versa. Okay. So that's all about the two time scales, GPS and INSS time scales. Do you have any question on this? If not, I'll move on to a different topic. Okay. Next, we are going to discuss some important properties of the C code. This will help you understand how using the code it is possible to uniquely identify a satellite. So we know that these codes are also called pseudo-random noise codes. Another term for the code is ranging code. We know why it is called pseudo-random noise. And the reason for calling it the ranging code is that using the code, later we'll see that it is possible to find the range to a satellite. The pseudo range measurement that we talked about is actually determined using the code. Okay. The code takes binary values. Either we can have plus minus 1 representation or 0 1 representation. Binary values. And one pulse is called a chip. Although we are going to talk about these properties using the CA code, this discussion also holds for other codes. Okay, these properties are present in other codes as well, but the parameters are different. Since we consider only CA code processing in our subsequent discussion, we will talk in terms of CA code, but these properties are present in other codes as well. The chipping rate is 1.023 megahertz, meaning this many chips are there in a second. Code period is 1 millisecond. Now, if there are 1.023 into 10 to the power 6 chips in a second, how many chips are there in a millisecond? Nobody can answer this question. How many chips are there in a millisecond?
Uh, 1023.
1023 chips are there in a millisecond. So in a code period, 1023 chips are there. Okay. Let's call this number capital N. Okay. For other codes, we will have different numbers. Let's represent a single chip graphically. So this is the time axis, and let's call P of t as P of t is just a single chip. So this is Tc by 2, this is 0, and this is minus Tc by 2, where Tc is the chip width. How can we find the chip width? What will be the chip width for this CA code? Somebody else? Is it possible to find the chip width? Chip width is basically the duration of the chip. What is the chip width for this CA code? How can we find the chip width? Duration of a single chip. We know how many chips are there in a second, right? So nobody can answer this question. Is it so difficult? Are you following or not following? Tell me clearly. If you cannot answer this question, then I should assume you are not following anything.
Ma'am, 1 by frequency.
This is the chip width in seconds. Okay. Now we can also normalize the time scale using the chip width and show the chip. In that case, P should be written as P by Tc because we have normalized the time scale using the chip width. Sorry. This will be half and this will be minus. Now how can we represent the chip when it's shifted in time? So let's say this chip here has shifted by say N chips, okay, and then we want to show it in the normalized time scale. So this will be shifted. The center line, which was 0 here, this will be shifted by L. Okay. Now a code period has 1, 0, 2, 3 chips in case of CA code. So basically we have a sequence of, I'm giving some representative sequence. Okay, don't think that this is the sequence following. So something like this you can assume. So this is minus, plus 1, this is minus 1. So here it is 1, 1, 1, and 2 times minus 1 here. Then again minus 1 here. So let's say this is the sequence. Okay. And there are capital N chips in 1 millisecond, in one code period in case of the CA code. Let's denote one code period as x of t. So x of t has capital N chips. Okay. And we'll mathematically represent as so for the time being, ignore this Excel. You just see what I have done. So I have put summation here. L is equal to 0 to n minus 1 because there are capital N chips. And when n is equal to 0, we basically have this one. When n is 0, we have this one. When n is 1, it will be shifted by one chip. Here I have shown how it will look when it is shifted by L chips. Okay. So this is the representation we use here, and XL can take on one of these two values, plus minus 1. Here we are assuming this plus minus 1 representation, not 0 1 representation. Because if we use the plus minus 1 representation, we can conveniently use arithmetic multiplication to represent the signal. So XL will take either plus 1 or minus 1 depending on the sequence of the C code. Okay, so it can be either plus 1 or minus 1, and then we have this one. So this is actually one code period, complete code period, because it has all the chips, N chips, capital N chips in the code period. Okay. Now we know that there is a one-to-one relationship between time domain and frequency domain. Earlier we discussed that in the context of signal power and power spectral density, from the frequency domain we can infer important time domain properties of a signal. The same also holds in case of the CA code or any code. Okay. So by seeing its frequency domain response or frequency domain characteristic, we can interpret some useful, derive some useful information about the code. Okay. Now the parameter which is most important in the frequency domain is called null to null bandwidth. Null to null bandwidth is determined from the frequency, or I'll say I'll write FFT or Fourier transform of a single chip. Okay, so let's denote this as capital F of this. I need to take the Fourier transform. Now we are considering a single chip, so we just need to do the integration from minus Tc by 2 to plus Tc by 2. Elsewhere it is 0. So this will be reduced to minus Tc by 2 to plus Tc by 2. And within this, it can have one of the two values, plus or minus. Now since we are interested in actually the amplitude, it does not matter whether it is plus 1 or minus 1, we just need to consider plus 1. Okay, and if you do the integration, you will find that it is equal to okay. Now this function sin pi f tc by pi f tc has a mean. Okay, we basically have sin, let's say sin y by y, and this is called sinc function, sinc y. Okay, so using this convention, the mod is this, and it looks like this. Now we are plotting against the frequency. Okay. So at this point it is Tc, and here it is 1 by Tc, and here minus 1 by Tc. So this width is actually 2 by Tc. This is the main lobe of the sync function, and these are all side lobes. Okay. And this one, the width of the main lobe is actually null to null bandwidth. And we see that it is equal to 2 by Tc. It depends on the chipping rate. So basically, it is proportional to the chipping rate, because 1 by Tc is the chipping rate. So in case of CA code, it is 2 into 1.023 megahertz. In case of PY code, which has a chipping rate of 10.23 megahertz, null to null bandwidth, so I'll just call it BW, okay? So BW is 2 times 10.23 megahertz. So the higher the chipping rate, the more is the null to null bandwidth, okay? And later we'll see that the higher the chipping rate, the better is the range accuracy. We noted that using the code we can derive range to a satellite. We can find the range measurement to a satellite. And later we'll see that the higher the chipping rate, the better is the ranging accuracy. Okay, so if we do not know the chipping rate of two codes, if we just see the Fourier transform of the two codes and see the null to null bandwidth, from there itself we can conclude which chip will give us a better ranging accuracy. So if you just see the sync pattern of the PY code and the CA code, you will see that the CA code has a narrow null to null bandwidth compared to the PY code. PY code null to null bandwidth is 10 times more. Okay, so given the sync pattern, the Fourier transform of a single chip, even without knowing their chipping rates, we can make out which chip will give us better accuracy. In fact, when we see the GNSS spectrum, we actually note the sync pattern. If somebody asks you about the GNSS spectrum, you need to actually point to this sync pattern. And from the sync pattern, we get all this useful information. Okay. See, here we have actually considered a single chip, but actually the code has multiple chips. In a code period, there are capital N chips, and the period repeats, right? So it continues in time. We have not considered all of them in this. It can be shown using the Fourier transform properties. It can be shown that if we consider, say, n chips in a code period, and also the navigation data. If you recall the signal structure, both code and data are multiplied to the carrier. Okay, so if you consider the complete signal structure, you need to consider code, data, and carrier. Here we have just shown the Fourier transform of a single chip. So let's go one step further and see how this Fourier transform would change if we consider the case when a single chip is multiplied to the carrier. And for simplicity, we will not also consider any offset. No offset is considered, because they have subtle effects, not any significant effects. So for simplicity, we will ignore their effect. Now we know the Fourier transform of this. and what we want to find is how this whole thing looks in the frequency domain. This can be easily obtained using some properties of the Fourier transform. So when you have the Fourier transform of a signal and if you multiply cos or sine to it, it actually gives you two replicas of the Fourier transform of the original signal centered at plus minus FCA. So we have this sync pattern, and the sync pattern will be doubled. One will be centered at plus FCA and the other will be centered at minus FCA. So here actually we are plotting the Fourier transform. So let's call this A of t. This one, and the center point is now shifted as plus FC on the right side, and on the left side it is at minus FC. Okay. So we have considered the carrier and one chip, but the actual signal has multiple chips, and also the period continues in time. It is repetitive in nature. One period gets over means another new period will start, right? So it continues in time. But we are not bothered about their effects because using the Fourier transform, it can be shown that when we consider the effects of, if you consider the signal for ith satellite, power will just amplify the whole thing. We are not bothered about this. Then we have this CI, this is the code. Then we have data, and then we have this cos term, right? So we need to, in the actual signal, we need to consider data. We also need to consider multiple code periods. It can be shown that if you consider their effects, the amplitude will be modulated, okay? It will superimpose a fine structure on the sync pattern, and also we'll have a series of delta functions. So the blue shows effects of multiple chips nav data and multiple code periods. I'm just writing PER. PER stands for periods here. Okay. Similarly, on the left side also we'll have something like this. Okay. So the effects of multiple chips, multiple code periods, and nav data basically impose some fine structure onto the sync pattern. But the dominant shape here still is the sync pattern. That's why we do not consider their effects, just in case it comes to your mind why we have just considered the single chip to determine the null to null angle. I'm telling this. But it's not possible to do the detailed Fourier transform and show that they have subtle effects. I'm just noting this as a passing comment. That they have subtle effects, so we do not consider them while determining the null to null angle. Okay. Any question? Next, we will talk about autocorrelation. We will not be able to complete this. We will continue in the next class, next week. Tomorrow you have the presentation, so tomorrow no class, only the presentation, no theory class. Next, we are going to talk about the autocorrelation and cross-correlation properties of the code. Autocorrelation measures and this will tell you how using the code we can find a satellite uniquely. So autocorrelation measures the similarity between any waveform and its time shifts or time shifted version. On the other hand, cross correlation compares a given waveform with all time shifts of another waveform. So in case of the autocorrelation, we consider the same waveform and find the similarity of the waveform with different time shifts of it. Whereas in the cross correlation, we compare two waveforms, two different waveforms. Okay. We'll first discuss the autocorrelation. Autocorrelation, for our discussion here, is given as so let's say it is the autocorrelation of say kth code. Okay. So small x is one code period. Tau is the time shift. Earlier also we discussed or defined the autocorrelation using random processes. In this case, we are actually approaching it in a different way, but it can be shown that whatever we defined earlier also holds here. Okay, so don't think that they are two completely different definitions. That is not the case. Here, for simplicity purposes, we are adopting this definition. But the definition that we discussed earlier can also be applied here. Okay. But then the treatment would be more complex. That's why we will not go down that path. We'll use this simple definition, which is an alternative one, to determine the autocorrelation and cross correlation of the code. Okay. That's it for today. We'll continue next week. Tomorrow you have the presentation. Each person will get about 10 minutes for the presentation. And this will be followed by a 5-minute question and answer. And Shujit needs to send all the results in advance. Before class, you should send me the results. Okay. So basically, you put all the plots in a PDF and then send me. In case I need some clarification, you have to share your screen and show me. But to the extent possible, I do not want you to share your screen because that takes time and the quality is also not good. Okay, fine. Any question? No question means you can leave.
Thank you, ma'am.